charms of earth, farewell, your springs of joy are dry. My soul now seeks another home, a brighter world on high. I'm a long time traveling here below. I'm a long time traveling away from home. I'm a long time traveling here below to lay this body down. Farewell, kind friends whose tender care has long engaged my love. Your fond embrace I now exchange for better friends above. I'm a long time traveling here below. I'm a long time traveling away from home. I'm a long time traveling here below to lay this body down. I'm a long time traveling here below. I'm a long time traveling away from home. I'm a long time traveling here below to lay this body down. To lay this body down.
Well, those harmonies, that's very moving. I'll pick it up with the next song. We'll play some Godsmack or Guns N' Roses or something the next song, but I like all kinds of music and love, that was 3-part harmony, 3 women, the Wailin, not Wailin, it's Wailin Jennies. Excellent group. Love their voices working together. In this unit, it's going to be a big unit. I'm probably going to break it up into 2 units because it is so big. There's some calculations involved. We're going to be talking about ventilation systems. First of all, I want to give you an overview of ventilation. It is the engineering control, the preferred engineering control for managing airborne hazards in the workplace. With effective ventilation systems, we can manage toxic gases and vapors, flammable gases and vapors, airborne particulates like silica or asbestos. High heat and humidity can also, important variables that sometimes get overlooked, can also be managed with effective ventilation systems. Even minor things like nuisance odors. A worker that is exposed to nuisance odors, they may not be as focused, they may be more prone to accidents. The odor itself may not be a hazard, but the distraction of a nuisance odor could be a hazard. But we can use ventilation systems to address this as well as these other airborne problems in the workplace. This kind of goes along with heat and humidity, the growth of mold and fungi in the workplace, and also ventilation systems can be used to control bacterial and viral exposures in the workplace. We'll talk about that, and we'll talk about some of the filtration systems that have been developed in recent years. Some of it's really developed more rapidly because of COVID, but we'll talk more about some of those filtration systems and technologies that have been developed or more rapidly developed here recently. But a lot of different hazards can be controlled with a good ventilation system. If you have airborne hazards in your workplace, this is your go-to first step. Don't go to the respirators first. Go to ventilation first. Remember, we always want to start at the top of the hierarchy. Engineering controls, administrative controls, and at the very bottom, the least preferred would be personal protective equipment like respirators. Now, there are cases where, you use ventilation, but you still need respirators. But ventilation should be your first emphasis when it comes to controlling airborne hazards in the workplace. The general objectives of ventilation: maintain adequate oxygen levels, control humidity, control the concentration of hazardous substances, remove contaminants if possible. And that's what we're doing with local exhaust ventilation, is attempting to remove the contaminants. Not just control the contaminants, but remove the contaminants from the workplace. There are 3 types of ventilation that we're going to talk about. We're going to talk first about local exhaust ventilation. That's where we're sucking out the bad stuff, or sucking out bad air and replacing it with good air. We'll also talk about dilution ventilation. This will be a unit all by itself. This is where we bring in fresh air to dilute the concentration of contaminants in the workplace. And I'll talk about this again when we talk about dilution ventilation, but dilution ventilation is most appropriate when we have lower toxicity hazards at lower concentrations. If the airborne contaminant is highly toxic and or at a very high concentration, then dilution is probably not going to be effective. We have to look at local exhaust ventilation. Again, local exhaust ventilation, when we're talking about contaminants, is going to be the most effective because we're getting rid of the contaminants. We're sucking them out of the workspace, and we're replacing that contaminated air with good air. Then we'll talk about general ventilation. We'll combine dilution ventilation and general ventilation into one unit. Mostly with general ventilation, we're talking about controlling temperatures and humidities, non-toxic types of nuisances in the workplace. Still important though, like I said, temperature, humidity, nuisance odors, that's an important concern. Now, some safety professionals, they will lump dilution and general ventilation together. Some will use the terms interchangeably, but I like to think of them differently. Dilution, we actually have toxic contaminants. With general, we don't have toxic contaminants, but we have conditions that can be improved in the workplace. That's going to make for a safer workplace. We're going to be talking about the design of ventilation systems and the different components, the do's and don'ts, but just on a very superficial, basic level. Complex ventilation systems in workplaces, they are going to be designed by an engineer, and they're going to involve a lot of calculations. We're going to do some basic calculations when we talk about local exhaust ventilation, and also when we talk about dilution ventilation. But when an engineer is designing a system, it's all about the calculations for the most part, and the existing body of knowledge as far as what works in ventilation designs. And I'll talk about this again, but if we're in a workplace where there is a need for a complex ventilation system, we shouldn't be the one doing it. We should be managing the implementation, but we should be outsourcing the design to an engineering firm that specializes in ventilation systems. There are engineers that specialize in ventilation systems. There are engineers that specialize just in the fans. The fan is an important part of the ventilation system. There are some engineers, all they do for their entire career is design and test the fan systems that go into ventilation systems. Local exhaust ventilation, let's talk about it more specifically. That's going to be the focus of this unit, is local exhaust ventilation. With local exhaust ventilation, we're focusing on what we call point source contaminants. Contaminants that are generated from a specific operation, from a specific location, an identifiable location, an identifiable operation, or substance that's creating the contaminants. An example of a point source contaminant would be carbon monoxide from a generator. Silica, when we're cutting concrete with a saw, or we're smoothing concrete with a grinder. That is a point source of silica. Flammable vapors from gasoline or other chemicals. The gasoline, the vapors coming off the gasoline, that is the point source. As it evaporates, these vapors are forming, and there's a health hazard as well as a flammability hazard when we're talking about gasoline and many chemicals have health hazards and flammability or explosivity hazards associated with them. But would be another example of a point source. Zinc oxide vapors from welding. Welding operations, especially if you're working with treated materials like galvanized materials or stainless materials, they're going to create vapors and fumes and bad stuff that can lead to a variety of health-related conditions, up to and including different forms of cancer can result from vapors from welding. Now, zinc oxide isn't so much a carcinogen as, say, hexavalent chromium that's going to be produced when welding involves stainless steel. But zinc oxide, you're going to have welders developing metal fume fever, which is a pretty minor condition. It's a condition that they can recover from, but it's uncomfortable. The welders aren't going to be as productive. They're going to be more prone to make mistakes. They're going to be more prone to have accidents if they are suffering from metal fume fever. So I'm getting kind of away from the idea of point source contaminants, but let's get back to that. Zinc oxide vapors from welding is another example of a point source contaminant. With local exhaust ventilation, we're attempting to remove the contaminants at the source. Effective local exhaust ventilation will result in what I call a clean atmosphere that is safe for workers. For me, a clean atmosphere is below the action level, 1/2 of the PEL. And that's generally, it's not always 1/2 of the PEL is considered the action level, but for many contaminants, the action level is 1/2 of the PEL. That's what I consider a clean atmosphere, when you're below the action level. Now you can legally be up to the PEL, and from a safety standpoint, according to research that's been conducted, if you're below the PEL, you're not likely to experience any health effects if exposure is below the PEL. But we want clean. We want 1/2 the PEL, ideally. And we can do this with local exhaust ventilation systems. Whether it's carbon monoxide or zinc oxide or hexavalent chromium, there are ways to configure exhaust ventilation systems that will remove the contaminants. Silica is a big one that we've dealt with since 2017, 2018, the new OSHA regulations. We can effectively manage silica using exhaust ventilation systems. The components of a local exhaust ventilation system, and really these are the basic components of most ventilation systems, but let's just focus on local exhaust ventilation right now. Basic system components include the inlet or the hood that we have right here. This is where the contaminated air is sucked into the system. The fans are creating a negative pressure. That negative pressure gets the air moving through the system. There are various hood designs, and each hood design has its pros and cons as far as being effective. And we are going to talk about each of these components in more detail. This is just the introduction here. The outlet or the stack, this is where the contaminated air leaves the building or leaves the space. It's on the back side of the fan where contaminated air is discharged through a discharge stack. We have static or static pressure. Our pressure is positive on the outlet side. Negative pressure causes the air to be sucked into the system. Positive pressure is expelling the contaminated air from the system. The ductwork, these are the pipes and tubings and different components that connect all the parts together. Complex ventilation systems can, in large industrial operations, can the ductwork can be quite extensive, hundreds of feet, if not more, and all sorts of Ys and elbows and tubing and so on. We'll talk more about ductwork in this unit. The air treatment system, or the air cleaner, not always necessary, but in some cases it is necessary. There are different types of air cleaning systems. There are scrubber systems, there are particulate filtration systems, electrostatic precipitators, and the new one that's got a lot of attention since COVID-19 in 2020. It wasn't new technology, but it got a lot more attention in 2020 because of COVID, were the ultraviolet systems that can kill bacteria and viruses using ultraviolet light. And the goal here is, with the air cleaning systems, is to remove the contaminant from the airstream before it's discharged. Again, not always necessary. When we talk in more detail about air treatment systems, we'll talk about circumstances where it is necessary to have some sort of air treatment system. The fan, this is the heart of the system. This is what gets the air moving through the system. The fan generates negative pressure. Air moves from positive to negative pressure. So we get that negative pressure. The positive air moves is sucked into the negative pressure. Depending on the complexity of the system, there may be multiple fans that are driving the air and moving the air through the system. The last component that we'll talk about, and that I want to mention here, is makeup air supply. A properly functioning system must have air to remove. If the system is too efficient at removing the air, but there's no air coming back into the space, the system can become airbound. And when it becomes airbound, air's not moving. The rule of thumb for makeup air, our makeup air supply, should be 110% of the air removal rate. If we're removing 1,000 cubic feet per minute from the space, we need to have a makeup air supply supplying 1,100 cubic feet per minute. Here's an example of, I wouldn't say really a complex system, but this is an example of the ductwork and hoods in an industrial facility where they are doing galvanizing work. The galvanizing work is taking place under the hoods. Again, we have hoods here. Each of these hoods represent a workstation. We got a couple of more here. But these hoods are the intake ports for the exhaust ventilation system. We have branch ducts coming off of a main duct. The branch duct goes from the main duct to the hoods or the inlets, and then it's all being, probably in this system, it's being exhausted without air treatment. But this is just to give you an idea of what you're going to be talking about or looking at in an average industrial ventilation system. Really below average industrial ventilation system. This is not a really complex system. Again, average or a little below average as far as the number of components and the complexity of the system. When we come back in the next video, we'll talk more about the hood and the inlet and the different types of hoods that are available and the efficiencies of different types of hoods.